This lecture shows how Pearl's do operation can be done without knowledge of the underlying network. This presentation was prepared by Dr. Alemi. Pearl suggested the do operation as a method of identifying the causal impact of a variable, say treatment, on another, say outcome. Pearl's method was groundbreaking because for the first time it clearly provided a formal, mathematical, and probabilistically consistent method for estimating causal impact. Pearl showed that if we condition on the right set of variables, shown here as z, then the causal impact of treatment t on outcome y can be assessed through weighted conditional probability distribution of these two variables. The key is finding the right set of variables that remove confounding, allow estimation of true conditional effect of outcome given treatment. The first step in Pearl's do operation is to remove all descendants of treatment T. A descendant of T is a node that can be reached if we start from T and follow the direction of the arcs in the network. The idea that descendants of treatment, for example complications of treatment, should not be statistically controlled is well accepted. One should not stratify anything on the causal path from treatment to outcome, as that would distort the impact of treatment on outcome. The second step in Pearl's do operation is that one should select a set of variables that will block all the backdoor paths from outcome variable y to treatment variable t. Backdoor paths refer to nodes that start with outcome and follow the direction or against the direction of network arcs till one reaches to a node that points to treatment. First we move backwards from outcome to the covariate. Then we move from the covariate to another in the direction of the arc. Next we move against the direction of the arc from one covariate to another. All backdoors must end up with an arc pointing to treatment. All backdoors go through one parent of treatment. There are also many options for blocking a backdoor path. Here, conditioning on any of the three covariates may block the entire backdoor path. One set of variables that can block all backdoor paths is the set that includes all parents of treatment. Recall that the definition of backdoor path requires that the path goes through parents. If so, blocking all parents will block all known backdoor paths. In blocking a backdoor path, one may condition on a common effect. Conditioning on a common effect may open new backdoor paths. One has to block these new backdoor paths as well. In this network, we have blocked the backdoor path on a common effect covariate, which has created a new association between its two causes, so the backdoor is not blocked at all. When blocking backdoors, it's important to verify that no new backdoors have been opened. In the fourth step in Pearl's do operation, one conditions on variables that block new or previously existing backdoor paths. Then the effect of treatment on outcome can be assessed using the formula shown. This is a simple conditional probability of outcome given treatment and the variables that had confounded the impact of treatment on outcome. The z variables in this equation are the variables that block all existing or new backdoor paths. The problem with Pearl's step is that in many situations we do not know or cannot know the network structure, and yet we want to estimate the causal impact of treatment on outcome. For each step in Pearl's network-dependent do operation, there is an equivalent step using multivariable analysis. These steps take advantage of procedures initially proposed by Shojai and colleagues. They assume that the order of the occurrence of the variables are known. Inside electronic health records, this is easy to do as all events are date and time stamped, so we know the order of occurrence of the events. In step 1, we remove the variables that occur after treatment and are associated with treatment. These variables are in network terminology descendants of treatment. The multivariate analyst does not know the network structure, but does know the sequence of the events and the correlation among the variables, and therefore can carry out this step. In step 2, the treatment is regressed on variables that precede it. This step identifies parents of treatment. These are covariates that make all other covariates irrelevant. Lasso regression identifies a set of variables that are significant predictors of treatment and all other variables are irrelevant. Since all covariates occur prior to treatment, then Lasso by definition identifies parents of treatment without needing to create the entire network. In step 3, we check for new variables besides the parents affecting treatment. This is typically done through stratification. Parents are stratified and the impact of covariates on treatment calculated. If the impact is large and statistically significant, then these variables are added to the list of variables to be stratified. In the final step, the stratified impact of treatment T on outcome Y is measured using methods such as stratified covariate balancing. Here we show an example. We want to know the impact of citalopram on symptom remission. Citalopram is an antidepressant and has many covariates. There are many covariates, all measured at baseline before treatment. Lasso regression has identified 6 covariates that are parents to citalopram. 26 other covariates are irrelevant. Stratified covariate balancing has not identified any of these 26 variables have an impact on citalopram, so no backdoor is open. No new backdoor is open. We show the parents inside the Markov blanket and the rest of the covariates outside and before the parents. The covariates that are outside the Markov blanket are not related to treatment, as indicated by Lasso regression and verified by stratified covariate balancing. The propensity of use of citalopram depends on the 6 covariates inside the blanket. These known predictors of treatment are stratified, and therefore we are examining the effect of treatment within these variables. So these variables are also not distorting the impact of treatment on outcome. We can now safely examine the impact of citalopram on symptom remission across strata defined by the 6 parents of citalopram. It is possible to do the do operation without creating a network model. The sequence of events, Lasso regression, and stratified covariate balancing can be used to get